Hello everyone, welcome to the lecture series of Computer Organization and Advanced Microprocessors. This is our 14th lecture, and in this lecture we will learn about the logic family. We have already studied about the integrated circuits, and now we will see the different logic families of the ICs. Also we call it digital logic family. So let's start with it. Okay, so now let's have a quick look on logic family. So if we want to define the logic family, then it's a simple definition that a circuit configuration or arrangement of the circuit elements in a special manner. So we can say that the categories or the different types of the logic families is completely based on the arrangement of the components on it. So it's a simple definition, but when we talk about the digital systems, actually this is we need to understand that when we talk about digital systems, actually the digital ICs are the ones which make up the whole system. And suppose if all the ICs are of same logic family, then they are compatible to each other. Very obvious, right? If all the ICs are from the same family, means all the arrangements of the components are same in the ICs, it means they are compatible with each other and the intended logic functions are performed, right? Because we don't need to give any extra effort in that, or we don't need to apply any extra technique on it, because all are belonging from the same family, so they are compatible with each other, and we can achieve our goal, whatever the goal, whatever the function it is, we can achieve that. But in case what if IC is belonging to different logic family, so here we need to understand that suppose ICs are belonging from the different logic families, then in that case we have to make sure for the different compatibility interfacing techniques. So if we have a good interfacing techniques for a different ICs from a different families, then we will be able to establish the communication between those ICs, because both are belonging from different families, right? So it is important to understand the importance of the logic or a logic family, or the significance of the logic family, and that is the reason that why we must understand the different logic families, and so we can use the best combination of ICs when we are designing the digital system. Now the question, one question may be arise that what might be the consequences of choosing wrong combination, right? It might be comes into your mind that what if we have used two ICs from a different families. So the simple answer is it may not match the necessary capability needed, and the solution for that is simple, like we need some compatibility interfacing technique for that. So this is a simple and a brief idea about the logic family and the significance of the logic family. Okay, so now after having the quick look on the logic family and understand the significance of the logic family, now we need to understand that what are the different parameters which create the logic families, right? So what happens when you design, or when you produce any digital IC, so in that time you use different circuit configuration and different production technologies you use, right? So each of this approach is called the specific logic families, like what type of circuit configuration you have used, or what are the different production technologies you have used. So all these different approaches are called the specific logic family. And now the idea of having different approaches or the different logic families is that each ICs of same family, when fabricated, will have identical electrical characteristics, right? Because when you are producing when you are producing the ICs in a mass, in a bulk, right? So whatever the production technology you are using, or whatever the circuit configuration or the arrangement of the components you are applying, so it makes it makes a family actually. So the time when you are fabricating it, that fabrication will have identical electrical characteristics, and the characteristics which are bound to be identical are normally supply voltage, then supply voltage range, then speed of response, then dissipation of power. Also input output logic levels can be take in a consideration, current sinking capability, current sourcing capability, noise margin, fan in, fan out. Many different characteristics are there, or many different parameters are there for that. And so the set of digital ICs belonging to the same logic family are electrically compatible with each other. So this is the basic idea of the logic family, that what is logic family, then what is the significance of the logic family, and what are the different parameters which design the logic family, right? So keep this thing in mind, that the different circuit configuration and production technologies used in the production of the digital ICs, and this approach called the specific logic family. Now let's see what are the different types of logic family. Now we know that what is logic family. So logic family is the way to describe the internal circuitry of the ICs, right? And here we have different 7 basic logic families. There are many logic families are there, but the basic 7 logic families are here you have on the screen. So the digital ICs are designed using any of the either bipolar devices or the MOS. That MOS stands for the metal oxide semiconductors, or the combination of both. It depends that which type of ICs we are designing and what is the application. And so the logic families which fall under the first kind are called the bipolar families, and this include RTL, then DTL, then IIL, and then the TTL. These are the also ECL comes under the bipolar, and the MOS or CMOS, also there is a PMOS, then NMOS are there, all comes under the MOS family. MOS nothing but the metal oxide semiconductor. So here we have basic 7 logic families. RTL stands for the resistor transistor logic, DTL stands for the diode transistor logic, IIL stands for integrated injection logic, TTL, that is the transistor logic. Also here we have one example of TTL like 7400 and 5400 series transistors are the TTL type. Then ECL is there, emitter coupled logic, and also we have the MOS family that we call the metal oxide semiconductor, and the CMOS stands for complementary metal oxide semiconductor. You must have heard this CMOS technology. Remember when you turn on your computer, that old computers, there on the screen it was written that CMOS settings. You must have heard, or you must have seen this thing. So these are these basic logic families. We are not going to learn these families in the detail. If you want to learn about it, I'll provide the link, and also in given PDF you can learn about it more. Okay, so now time to learn about the different characteristics of logic families. Like, what are those different characteristics which actually make the logic families, right? So here we have basic or a total 5 characteristics: fan in, fan out, then power dissipation, then propagation delay, and the noise margin. Again, this is not our electronic subject, so we are not going on in that detail, but we'll just take a look on all these characteristics, and we'll just try to understand that what is the meaning of the characteristics, and how they make a different, how they create the different logic families. So let's have a quick look on the different characteristics. Okay, now let's understand the meaning of all these characteristics of logic family. As we know that there are five logic characteristics: fan in, fan out, power dissipation, propagation delay, and noise margin. So let's start with the fan in. So fan in is the number of inputs connected to the gate without any degradation in the voltage level. Just see the right side image. There is a small image of the fan in. What is the meaning? Fan in is the number of inputs connected to the gate. So as you can see in the image that there is a one NAND gate is there and there are n number of inputs are there, right? And fan in characteristic, what is the actually meaning of fan in characteristic is n number of inputs. When we connect to the gate, we don't need to change any voltage level, means there is no any degradation, even we don't want to do and even it will not do. So the degradation in the voltage, without any degradation in the voltage level, we can work with this gate. So that characteristic is called the fan in. Fan in means n number of inputs. If n number of inputs are connected to the gate but still there is no any degradation in the voltage level. After the fan in, we have a fan out. Fan out specifies the number of standard loads that the output of the gate can drive without impairment of its normal operation. We know that when we are working with the gate, it has to do some operation, right? But what is the characteristic of fan out means? When we talk about the fan out means number of standard loads that the output of the gate can drive. See, we know that when we work with the gates, we apply the inputs and based on the logic it gives some output. But it might be possible there is n number of loads, n number of outputs. It might be possible that your circuit or the device cannot handle that load. So fan out characteristic make sure that irrespective of the number of outputs, the number of standard loads that the output of the gate can drive, there will be no any impairment in its normal operation, means it will work smoothly, it will work perfectly. So that is the fan out. I repeat, fan out means what? Fan out means irrespective of how many outputs are there, there will be no any damage in its operation and that operation will work perfectly fine. So that is the fan out. Then we have a power dissipation. It's very simple. Power dissipation is a measure of power consumed by the gate when fully driven by all its input. When you design the gate, when you operate the gate, n number of inputs may be there, right? And when you supply the power current, when you apply the power, so power dissipation is nothing but the measure of power consumed. So just check that how much power your gate is consuming, that we call the power dissipation. When fully driven by all its inputs, means all the inputs are on or all the inputs are active. So power dissipation is a measure of power consumed by the gate when fully driven by all its input. Okay, then we have a propagation delay. Name itself says delay means something is going to be happen in little bit late, right? Okay, so the propagation delay is the average transition delay time for the signal to propagate from input to output when the signals change in value. It is expressed in nanosecond. Delay is delay is an entity which is related with the time, and the unit to measure the propagation delay is ns, that is the nanosecond. So as you can see in the image, there is a propagation delay. See that yellow bar. So when that yellow line is starting and then gradually it delays the operation, right? It delays the function. So the propagation delay is the average transition delay. Transition means when your device switches or goes from one state to the another, that we call the transition. So the average transition delay time for the signal signal, right? Because we know that signal travels from one location to the another location. And suppose there is a 1 0 is a signal, so 0 signal and the 1 signal. So when there is a transition between 0 and 1, so that we have to understand that 0 and 1 average transition delay time for the signal to propagate from input to output. When the signals change in value, it is expressed in nanoseconds. So that is called the propagation delay. Then the last characteristic is noise margin. So it is the maximum noise voltage added to an input signal of a digital circuit that does not cause an undesirable change in the circuit output. It is expressed in volts. So see what happens, there is one signal line and there is a one noise line, right? So when your signal changes its state, it might be possible that it generates some noise. So what is the limit, what is the margin of that noise? When we set that margin or when we measure that limit, we call it a noise margin. Means it is the maximum noise voltage. Means we can say that this gate or this device can handle this much of highest voltage, that we call the noise margin. So the noise margin is nothing but the maximum noise voltage added to an input signal of a digital circuit that does not cause an undesirable change in the circuit output. When you are inputting something, for example 5 volts you are applying, but it might be possible that sometimes 5 6 7 8 9 or a 10, but if you apply the 10, 11 volt, it might and there is a damage in the device or there is a change in the output. In that case we can say that 10 is a noise margin, right? Because we cannot go exceed that 10, so the margin is 10, so that we call the noise margin. So it's all about the characteristics of the logic families, and based on this characteristics we can bifurcate the different logic families. Okay guys, so it was all about the logic families. We have seen the different types of logic families, their different characteristics, and also we have learned about the what is the meaning of the characteristics, how does it work. So it was all about the logic families. So happy learning, keep learning. Thank you.